My name is Narendra Atmakuri. Currently working at Panasonic Avionics as a principal architect. Earlier, I worked on building the autonomous driving stack, where I would like to touch upon how DPU can be adopted there and how this autonomous driving stack would be get beneficial from DPUs. And uh, the aspects of DPU in this aspect. So a brief about me. So I have worked in building the Galaxy phones at Samsung, and I also worked at companies like Qualcomm, Samsung, Broadcom, uh, and at Aptiv I was working at building the autonomous driving stack, where we were working on building the adopting the software-defined vehicle platforms, where we see a lot of computing power is needed, and the real world impact is like how you can do the more compute resource optimizations and bring the AI based and ML based perception stacks, and how better you can perceive the environment and take the right decision in the perspective of autonomous driving stack. And currently, I'm working on building the new modernization stack for in-flight entertainment and connectivity and networking. And I spoke at a lot of events related to software-defined vehicles and a lot of new technologies. So traditional, I'll speak a little bit about how software-defined vehicles is evolving and how it can be related to DPUs and the needs for high computing power and need for the offloading the infrastructure activities. So you see earlier in automotive industry, where you used to have hundreds of ECUs and a very complex way of interconnecting that, and the actual computing is very computing is very like it's distributed across many small ECUs. And now you see the shift, like where from the hundreds of ECU to a central computing unit, or you can see HPC, high performance computing, where it wants to have a zonal wise and make the centralized processing so that it can process in a better way and reduce the overall complexity and overall weight, and the easily manage over the software upgrades and a lot of new cloud native technologies, and make it in the more maintainable and easily scalable. So the market transformation, you see it's going to be reached by 80 plus billion by 2030. And you see in a vehicle overall cost, the software cost is going to be more than 40% of the total vehicle value. Architectural evaluation in automotive industry is going to be like a ADAS and autonomous driving all the way from level 2 to level 4 and level 5, and digital cockpit, connectivity and telematics. All this needs a very high computing power and a mixed criticality kind of the architectures, where you will have a parallelly running safety critical and non-safety critical applications running in a same computing environment side by side. And key enablers for this technology is like a sensor fusions, AI/ML perception, real-time operating systems with a high determinism, and hypervisors, containers, and cloud-native technologies, and adopting into the automotive safety standards. So I see DPU is a kind of the third computing pillar, where you will have a multi-core CPU with high performance network interface and flexible accelerating engines for AI and ML and security and storage. And it is actually complementing the computing models of CPU, GPUs, and specialized in a data movement and infrastructure offload. And a lot of critical capabilities that we can see, like open vSwitch accelerations, RDMA transport, GPU bypass, TCP offload, network virtualization, precision timing, and security operations, storage operations, and smart NIC integration, where you can see programmable data plane while freeing the CPU and GPU resources. It is used for the critical functionality like determinism behavior, and make it a resource available for CPU, GPU for the other things that it needs to do. And market momentum, I see major vendors like NVIDIA, Intel, AMD, Marvel driving adaptations across hyperscale data centers. A very brief about OPI project to accelerate DPU and IPU adaptation. To prevent a vendor lock-in. And I see like a 5 working groups, make it a more independent underlying part of it. And develop is a more programmable and isolate, compute, is a aggregation independently intelligent subsystems rather than directly coupled, make it is a more decoupled way. And strategic objectives is like use the network storage, security, and cloud native infrastructure to develop the DPU devices without a hardware investment. Automotive relevance is like I would see like OPI standards can be, architectures can be applicable to software defined vehicles as automotive is adapting to the data center technologies for in-vehicle computing. So the relevancy for this technology and automotive. So I would say these are the key pointers, like architectural alignment. Modern vehicles are generating like a 5 to 20 terabytes of data daily, and from sensors, and we need a data center class of processing capabilities, and offload and acceleration, where you need a DPU to offload a vehicle to cloud communication and the sensor data processing and a lot of network processing and network security management and storage management and real world validation. So this Calary MPPA DPU is already deployed and got some kind of the good results by deploying a DPU in this aspect. And security, so this will enable a zero trust security architectures with doing a lot of security processing, which is offloading to DPUs. And cost and power benefits, you see, the power reduction and consolidating the functions and DPU reduce overall system cost by around 30 to 40%, and while improving the functionality. So just a brief overview on automotive AI workloads, edge intelligence powered by DPU acceleration. We can see projected KPIs. In automotive, we need a very deterministic and time-sensitive operations would happen. Examples are like autonomous system computing to be able to brake or understand automatic emergency braking feature. It should understand, and there is the time required is very, very less, sub 100 milliseconds time frame that it should be able to respond. And perception stack optimization. So where I see ML models and DPU style acceleration can improve the object detection accuracy and identify the environment in a more efficient way. And you see heterogeneous computing. So DPUs can be seen as a complementary to existing GPU-based AI training, and a lot of things like the data ingestion, pre-processing, and the data movement between performance domain to DPU domain and all, and scalability and flexibility. So it can see like easily we can use OTA updates and the AI models and algorithms without hardware changes, supporting a continuous improvement in the field and throughout the vehicle life cycle. So this is a brief about zero trust security. So we can see zero trust principles, like DPUs can play a very good role to actually enable a zero trust principles and completely offloading or taking care of the security functionalities all the way from the establishing the root of trust and all the way at security at each level. And cyber security aspect, like where V2X, OTA updates, and cloud connectivity, third-party applications, inline security processing. So UC DPUs can perform IPsec, TLS encryption, decryption inline at a line rate without impacting the application's performance, and enabling end-to-end encryption for vehicle communications. And this is also enables isolation and segmentation, where DPU virtualization capabilities enable a micro segmentation of vehicle networks that will enable to run a different networks and different networking segments within the vehicle environment. And you can have a safety critical ADAS functions, and from infotainment systems, you can separate and running all the critical and non-critical side by side. So this is automotive adaptations. How it can be done is like the safety relevant advancements like ISO 26262 and environmental robustness. So you can see in a vehicle environment, we wanted to have an environmental robustness and a real-time determinism, where you see automotive workloads demand a guaranteed worst-case execution time and bounded latency. DPU architectures must support a real-time scheduling, power and thermal constraints. So I would see some of these more specific to automotive requirements, and this should meet, I mean, to consider all these. I would say phased adaptation that can be seen like a apply this adaptation in a non-critical environments like infotainment and connectivity area, where it can slowly adapt it to ADAS acceleration and safety critical integrations. So I would see building a future together, how it is relevant with OPI goals. I would see, I mean, join a OPI working groups, contribute automotive use cases, and think in the perspective of how it can be adapted into automotive and non-extended as a avionics, in-flight entertainment aspects, and use case and developer platform working groups to ensure standards address SDV needs, and a developer reference implementation. So create automotive specific DPU reference architectures for demonstrating a sensor fusion, AI acceleration, and zero trust security for autonomous driving systems, and cross-industry collaboration. So bridge the data center and automotive communities through joint workshops, proof of concepts, and the standards between OPI and a lot of automotive standards like AutoSAR and SOFI. So I would see like accelerated pilot deployments. I would see, I would comment as vision for 2030, standardized DPU architectures, become a foundational to software-defined vehicles, and a seamless interoperability across OEMs and suppliers, and accelerate innovate cycles, and reduce the development cycles from long cycles in automotive to months, and build the safer, more secure, and highly efficient way of offloading the infrastructures, and build the systems that will continuously improve and mobility experience to the billions of people worldwide. So any more details? My contact details are there. Thank you.
We'll do a quick question, or we have lunch. No, a very innovative thinking, right? Is there any cost analysis that you have already done? This is very, detailed already, but if not, I think we should talk offline.
Cost analysis.
In the sense that, yeah, I mean, maybe two questions, right? One is cost analysis of what else is being used, because automotive is a very cost sensitive area, and DPUs are, as volumes pick up, maybe, we'll get to those numbers, right? So that's one.
So I would see in terms of the cost analysis. So as a overall, the value that it is bringing versus how it can be adapted into the bigger automotive product bill of materials, or the overall cost of the automotive platform, I would definitely see kind of the very, I mean, good use, and cost will overall make it a bring down overall perspective, the functionality that it is bringing, and the way that it is being used to build the futures like the virtualization and micro segmentation and the mixed criticality applications. So earlier there is a lot of software cost to improve the technologies, and where we can see offloading this all to the DPU kind of environments, where we can see lots of cost saving. So I would see the cost implication as the hardware cost versus the overall engineering cost and the software cost. So I would see a good benefit in adapting to this, where you can have a lot of offloading to the hardware and bring this software functionality very cost. You see engineering cost, NRE cost are so high in this space, and the cycles of the automotive cycles are very long. So those are all going to be very good impact of bringing all those to the capability to DPU and offload the infrastructure. You can decouple on the software stack and make it a more portable software modules that highly help the software industry.
Thanks a lot, Narendra. Really appreciate your